Okay, so let's get started. Before I continue on the content of the lecture, so let me say something about the syllabus of the final exam. Okay, so I'll upload this to Blackboard today. You can see that it will cover, okay, so all the way from chapter 2 to chapter 6. However, notice the details. Okay, so I'm not going to test all the parts. Okay, so in every chapter. Okay, in chapter 2, you can see that I will only test part 1 and part 3. Okay, so that is what is part 2? Part 2 is about the force of constraint using the Lagrange multiplier, right? So you don't need to worry about that in the final exam. Okay, so some hints for you here. Okay, so what formulas or what equations you need to at least memorize. Okay, so Lagrangian in Cartesian and cylindrical coordinates. Okay, Lagrange equations and generalized momentum. Okay, at least memorize these. Okay, and then chapter 3, central force motion. I'll only test you part 1. Okay, so that's about the basic properties of the motions of the elliptical orbits or other kinds of orbits, right? So and you won't see part 2, part 3. So what are part 2, part 3? Part 2 and part 3, they are about the reduced mass, right? So two-body motion and stability of circular orbits, right? So oscillation. So those are in the part 2 and part 3, but those you don't need to worry about. Okay. And hints. Okay, so you do not need to memorize this equation of orbit. Okay, so if you need to use it, I'll provide that to you. Okay. And chapter 4, coupled harmonic oscillators. Okay, so I'll test you all 3 parts. Okay. So I would say that in this chapter, okay, so it's a chapter that is quite straightforward to study, right? So because the situation is always very similar, right? So you have a few particles connected with springs, right? So and the way to solve the whole thing is always just the same standard procedures, right? So and you just need to be familiar with finding the eigenvalues and eigenvectors. Okay. And then chapter 5. So actually, chapter 2, chapter 3, and chapter 4 are something that you have been tested in midterm already. Right? So at least you have experience. Okay. So chapter 5, Hamiltonian mechanics. So this was not tested in the midterm, right? So and here I will test you part 1, 2, and 3. Right. So part 4 is excluded. I've already told you that when I taught that part. Right? So that part is about a canonical transformation. Okay, again, hints. You should at least memorize these the following formulas or equations. Okay. So the expression for Hamiltonian, right? So Hamilton's equations of motions and Poisson's bracket. Okay. And finally, chapter 6. I'll test you on part 1, part 2, part 3, and part 4. Okay. So part 5 is excluded. Part 5 is just about one example, which is the one important problem, which is the Foucault pendulum. Okay. So that one is excluded. And again, hint, you need to at least know, right? So how to write down the fictitious force. Okay, so in linearly accelerating frames. Okay, as for the rotating frame, have to know how to find the Coriolis force. Okay. Memorize these formulas. Okay, any questions about the final exam? So I'll post it on Blackboard soon. Okay. Okay, if not, let's continue on the chapter of rotation of rigid body. Right. So last time I almost finished this part 2, right? So I introduced how to find the angular momentum of a rigid body. In particular, you learn something new, right? So the so-called the inertia tensor. And I also told you how it is related to the so-called moment of inertia that you have learned in last year, right? So essentially, moment of inertia is the principal, is the diagonal element of your inertia tensor, right? So when you are in a coordinate system where the 3 coordinate axes are parallel to the principal axis of the rigid body that we are considering. Okay. Okay, so and let me finish this slide and then I'll move on to the next part, part 3 of this chapter. Okay. And again, so this is a result that you have kind of seen before, I believe, but you might not have formally have seen the proof. Okay, so that's the Newton's second law for rotation. Okay, so that is torque equals rate of change of angular momentum with respect to time. Okay. And in particular, right, so the vector notation are important. Okay, okay, so how do we prove this? Okay, so let me just do this. So again, I'm going to start with a system of particles. Okay, so this result can be used for a system of particles, and no matter whether the system of particles together form a rigid body or not, right? It does not have to be. So for a system of particles, at least you are also familiar with the following, right? So we just talk about the linear acceleration of the particle, then what you have is the following. So the total external force is equals to the total mass of the system times the acceleration of the center of mass of the system. Right. So this is something that you're familiar with and we have also used before. Okay, so to set up this proof, what we are considering is the following. Okay, so first of all, I actually have two coordinate systems. Okay, so one is again the xy, right? So xyz, but let me just draw xy, and this is the origin. So this is just a fixed coordinate system. Okay. And then I have another coordinate system, which I call x prime, y prime, z prime. And then the origin is at O prime. And then the vector pointing from O to O prime, I will call that R naught. Okay. And then the system of particles. So a bunch of particles over here, like this. So if I use the prime coordinate system and describe the position vector of one of the particles, say this one, right? So then the position vector that I'm going to draw is like this. Okay. And this, and I'm also going to draw another position vector, which is measuring relative to the fixed coordinate system. Okay. So this I call Ri. And then the blue one is Ri minus R naught. Okay. Okay, so the prime coordinate system by itself can be moving as a function of time. It can be accelerating. It can be doing anything. Okay. So now, if I want to measure the angular momentum of these I particles, right? So using the prime coordinate system, okay. Then what I have is this expression here, right? Just one of them. Again, I'm just using the R cross MV. So this is what I have. Okay. And then if I want to express the total angular momentum of the system, it's just a vector sum. Okay, so the sum of this Ri minus R naught cross Mi times Ri dot minus R naught dot. Okay. All right, so again, so notice that this angular momentum is measured, okay, so in the prime coordinate system. So now if I do a dLdt, right, just taking derivatives for this expression here, right, so and then you just use the product rule, then this is what you have. Okay. So now here you can see that I have written down some terms. So in terms of external force and internal force. Okay. First of all, if you just look at this first term here, you notice that this is 0. Right? So because this vector is identical to this vector, the vector do cross product with itself, of course, is 0. So this first term is 0. So I write it here. Okay. And then next, right? So this MIRI double dot, right? So that is talking about the acceleration of the I particle, right? So, and that must be equals to the net force acting on that particle, right? So that must be the F external I plus the F internal I. Okay. So then the first term, so this Ri minus R naught cross F external is written here. And then the last term, this one cross Mi R naught double dot is written here. And then what about this term? So this term cross the internal force, summing up will be 0. Okay. So you might need a minute to actually think about that carefully, right? So if I just, first of all, if I just tell you that the sum of F internal is 0, first of all, if I just tell you this, you don't have any problem with this, right? So this is something you have seen. Okay. However, what about the sum? Now, what I'm telling you is that not just the sum of FR, but not just the sum of the F internal, but it's the following. So now I'm telling you this. So this is 0. Okay, so that then why is that true? Okay. So just consider, you just need to consider any pairs of the particles in the system. Okay, so let's say I consider this particle and this particle. Okay, and then suppose, right? So there's an internal force acting on this particle by this particle, and then likewise there's an internal force acting on this particle by this particle. Just action and reaction, right? So then let me just draw it this way. So this F over here, and then here I have the minus F, right? And then this is, let's say this is the I particle, right? So this is a J particle. And therefore, right, so here is the O prime. And then over here, I have the Ri minus R naught. And over here, I have the Rj minus R naught. Okay. Okay, so now you know that this force and this force, they have equal magnitude but opposite direction, right? So if I add this force and this force is 0, but what I'm doing now is that I take this cross product and then add this cross product, okay. And they will still be 0, right? So why is that? Because this position vector cross this F, you know that the magnitude is the following, right? So it would be taking this distance times this F, right? So the perpendicular distance. And similarly, if I do if I cross product using this position vector and this F, then also, right? So you are taking this distance times this F, right? And this distance here is actually the same as this distance here, right? So although this length and this length is not the same, but we are just taking the perpendicular distance, right? So because of the fact that these two distances are the same, and then these two forces have the same magnitude, that's why the cross product cancel. Okay. So therefore, this whole term summing up will be 0. Okay. So therefore, I don't need to worry about this term here. So then we are almost at the final result. Okay, so this is the two sum that I have. And then finally, for the second term over here, I write it as this capital M times this capital R minus R naught. Okay, then cross the second derivative of this R naught. Okay. So what is capital M? Okay. So capital M is the total mass of the system. And this what is capital R? Right. Right. So that's the center of mass position. Okay, so now if you look at the final result, right? So dLdt is equals to this term minus this term here. And if you only consider the first term, this is exactly the total torque, total external torque acting on the system. Right. So then that will finish the proof. But actually, there's one thing here. That's actually a second term. Okay. So therefore, in order for this formula to work, so this formula here, so that is the dLdt equals total external torque, we actually require the second term to be 0. So under what circumstances the second term will be 0? So there are a few possibilities. First of all, the capital R is equals to R naught. Then this capital R minus R naught is 0. That is to say, if you pick the coordinate system, the prime coordinate system, to be originated at the center of mass of the system, then you can use this torque equals dLdt. Okay. If you don't satisfy this condition, there's also another choice. Another choice is that if R naught double dot is 0, so that's this term, R naught double dot is 0, then you can still make this second term 0. So what does that mean? So that means that the origin of your prime coordinate system is not accelerating. So finally, there's also a third condition that you can use, but this one is usually not how we use it. It's not usually not being used. Okay. So just either look for the first or the second requirement. And in fact, you realize that these tools are very common choice, right? So in many problems, we do select the center of mass as the origin of our coordinate system. Okay. And also, we do, at least except for one of the chapter, we do always have the coordinate system to be not accelerating. So then therefore, one thing you need to be very careful, okay, is that when we use accelerating coordinate system, like what we did in chapter 6, when you actually use that, that means you are not satisfying this condition 2. Then if you still want to use this torque equals dLdt, you have to use condition 1. That is, you need to make sure that the origin of your coordinate system is at the center of mass. Okay, so then this remark here is somehow related to the last chapter. Okay. Okay, so now we are really ready to explain some physical phenomena. Okay, so using the tools that we have learned. Okay, so in particular, I'm going to talk about the so-called the rotation and precession. Okay. So the system that we are going to consider is the so-called symmetric torque. Okay, so we are not considering any arbitrary shaped body. Okay, so we are considering these kinds of bodies. Okay, just from your sense, you know that they have one common feature, is that they all have one symmetry axis, right? And for these kinds of bodies, so, and if you take the coordinate axis to be the following. So if you take the coordinate axis like this, like this. So let's say this is the center of mass. And then this one also like this. Again, this is the center of mass. So that is, if you are working with the coordinate systems where the origin is at the center of mass of the body, and these three axes are parallel to the principal axis of the body, then your inertial tensor is written like this, right? So in particular, for symmetric torque, okay, so two of the values for the diagonal elements are the same. Okay. So this is what we mean by symmetric torque. Okay. And that's actually quite easy to understand, right? So this is let's say, for example, let's take this plate or this cylinder as an example, right? So what is this I3? This I3 would be the moment of inertia when you try to, right? So rotate the body, right? So about this axis, this Z axis. Okay. So and then this I1 and I2, which I call I, are the moment of inertia when you try to rotate about the x-axis and about the y-axis. Right. So by symmetry, you can see that, right? So although you don't know the value, you might not remember the value, but by symmetry, you can clearly see that the rotation about the x-axis and the rotation about the y-axis will correspond to the same moment of inertia. Right. So, but then the z-axis is the one that is different. Okay. So in particular, we will work with this plate. So let me give you the real numbers. So in this case, the Ix and Iy are both equals to 1 divided by 4 mr squared. So r, of course, is just the radius of this plate. And then the Iz is 1/2 mr squared. Okay. So the first example we'll look at is to look at this plate, study the motion of this plate. Okay. So in particular, we'll consider two scenarios, the following. Okay. So the first one that we'll consider is that with this plate with no external torque. Okay. So that is a dLdt is 0. Okay. So dLdt is 0. So well, according to your common sense, you might think that then probably nothing interesting is going on, right? So angular momentum is constant. However, let me show you a short video first. Okay. So this is a person holding a disc or plate, just like this one, holding it like me, like what I'm doing, right? So it's just a camera from the top, and then what they try to do is the following. Okay. So try to throw it up and then spin it at the same time. So of course, the whole thing is doing a projectile motion because of gravity, right? So, but you understand, first of all, you understand that the gravity itself does not actually give a torque to the plate about the center of mass, right? So that center of mass motion is irrelevant in this picture. But what you can see is the following, right? So of course, the plate is rotating about the center, but then at the same time, the plate is not always exactly facing up, right? So as it rotates, the plate is also doing something like this. That's the so-called wobbling motion, right? So that is right. So mathematically, if you draw a normal vector to perpendicular to the plate, that normal vector is not always pointing up, right? So it's actually changing direction. Okay. So then this is the kind of motion that we are going to study. So there are two things. One is the rotation about the center, and the other is the what I so-called the wobbling about the center. Okay. So then see this slide. So then the quantitative, the qualitative description of motion, right? So it's just something that I just told you essentially, right? So rotation about its center, and at the same time is wobbling, right? So that is the orientation of the face of the plate is changing over time, periodically. And with this kind of motion, actually, the direction of the angular velocity is actually changing over time. Okay. So then you can see that this is not too easy to solve, right? So you could imagine, right? So even though that I'm not having this any external talk, okay? So now I am having a changing angular velocity. And what I want to study in particular is the following: is there a relation between the rotational frequency and the wobble frequency? So what is the wobble frequency, right? So because as I said, if you try to draw a normal vector to this plate like this, right? So then you know that sometime later, the normal vector pointing here, and then some later time pointing here, some later time here, and then at the end it's go back. So that is right. So the tip of the the normal vector of this plate is also forming a cone like this, and then basically the wobbling frequency or the wobble period is the time taken, right? So for this normal vector to complete one full cycle, right? So like this. So initially it's like this, right? So sometime later, this finally go back to this orientation. So that's the wobble period, right? So when I do this, I should also be spinning the plates, but you understand the idea. Okay, so actually, so just some interesting story. So this problem is kind of famous, is because of Richard Feynman. Okay, so in his book, surely you are joking, Mr. Feynman. He just shared a story. Okay, so he one day he was sitting in the cafeteria in a university, I suppose, and then he saw someone just throwing a plate in the air. So just like the YouTube video that I showed you, okay. And then that plate probably looks like the following, right? So just a circular plate, and then at the center of that plate, so there's kind of this medallion. That is the logo of this Cornell University. So there's a logo here. And then well, from how the logo turn, right? So you can see how fast the plate is rotating, right? And however, so he noticed that this rotational frequency, okay, so it's actually not the same as the wobbling frequency. So that's what he saw by eye, by observing this logo, okay, so printed on that plate. Okay, so and then he was trying to figure out, okay, so what is the relation between the two frequencies? Okay. So how to solve this problem? Okay, so we are going to define two coordinate systems. Okay, so one is the black one that you see over here. Okay, so the black one, that is just originated at the center of mass of this plate. And then the other one is the prime, the red coordinate system, which we also call the body frame. So this is the frame that is basically glued on the body itself. Okay, so the three axes are always overlap with the three principal axes of the plate. Okay, so the red one. So recall what we learned in the last previous chapter, right? So rotating frame. So this body frame is a rotating frame actually. However, in some sense, it is even more complicated. So in the previous chapter, when we talk about rotating frame, the omega vector that we consider is always just pointing in a fixed direction, right, and with fixed magnitude. But here, so I told you already that actually the omega vector is changing with respect to time. So that is, it is a rotating frame, but also the rotation vector, the omega vector itself is changing over time. Okay. But however, that's okay. Okay, so still a rotating frame, and the formulation that we learned from the previous chapter will still be useful. I'll show you when we use it. Okay, so now let's try to solve the problem, and I will show you two different ways. Okay. Okay, so of course, right, so to solve this problem, I have to first of all write down the angular expression for the angular momentum and the expression for the angular velocity, right? Now we are using the so-called the body frame. Okay, and let's say in this using the basis, using the unit vectors of this frame. Okay, so I'm able to express the omega vector as the following: omega 1 x hat prime plus omega 2 y hat prime plus omega 3 z hat prime. Okay. Again, want to remind you one more time is that when I say that I'm expressing the angular velocity using the basis vector of this body frame, okay, so it doesn't really mean that I am trying to observe the rotation in the body frame. So what does that mean? So if you are an observer that is standing on the plate, right? So you are basically rotating with the plate at all times, right? So you will actually not be able to actually measure that rotation, right? So because you are rotating with it, and unless you see something outside relative to you, otherwise, right? So you might not even notice that you're not rotating or not. Okay. However, that when I say expressing the angular velocity using the basis vector of this frame, that's not what I meant. Okay, so I'm really simply saying that I'm expressing the omega vector. Okay, so using the basis vector of this frame. That is, you imagine that I give you the omega vector already in the basis of fixed frame, okay, and then you change the basis to get here. Okay, so now angular momentum. So the reason why we want to use the body frame to solve this problem is because of the fact that the angular momentums can be expressed in a convenient way. right? So like this, because in this frame, there's no off diagonal element, right? So in the inertial tensor. So that's why it's relatively convenient to write down the expression for angular momentum. Okay, like this. So, and then I'm just going to manipulate the terms, and then we express it as this over here. Okay. So basically, you're just substituting this one into this expression here, and you can get this. Okay, so now I have L and I have omega, and you realize that the omega can be written as, right? So the subtraction of these two terms over here. Okay. So, and when I write it this way, so you realize that actually these three vectors, okay, so they are in the same plane. They are lying in the same plane. So that is, if I do a rough drawing, that won't be a very accurate drawing. So the Z is pointing this way. So the L is pointing up, and the omega is somewhere over here. Okay. So, but all these three vectors, they are on the same plane. So like this. Okay, so now recall something you have learned in the previous chapter. Okay. Because now we are in the rotating frame, right? So you remember that if you're in the rotating frame, then the time derivative of the basis vector is given by omega cross the basis vector itself. Okay, so like this. So then this dz dt can be written as, right? So this whole thing is omega, right? So cross z hat prime. And then the second term, the z hat prime cross z hat prime is just 0, right? So I only need to care about the first term. So like this. So the L, I'm going to write it as the z hat. Okay, so remember this z hat is this one, this black one. Okay, so this z hat cross z hat prime is not 0. Okay. Okay, so now we are almost done here. Okay, so now I'm going to make an approximation. Okay, so that is, I'm assuming that this wobbling amplitude is small. So that is the normal vector of the plate. Okay, so it's quite close to the perpendicular, the vertical z hat vector itself. Okay. So in that case, the L can be simply written as approximately equals to the I3 omega 3. So then this L divided by I is approximately given by this I3 omega 3 divided by I. And what is this I3 divided by I? So for this plate, so remember the I3 is 1/2 mr squared, and the I is 1 divided by 4 mr squared. Okay. So then that is a factor of 2. So then that is the 2 times omega 3. Okay. So that is the wobble frequency is actually approximately equals to 2 times the rotation frequency. Okay. So let me show you another video here to illustrate. So you can see this is a plate. Okay, so and there's a logo on top of the on the face of the plate. Okay, so if you look from the top, right? So at this moment, you look from the top, the logo is kind of like this, right? So the tip of that of the pattern is pointing kind of away from you. Okay. So and at this moment, right? So the plate itself is a little bit tilted towards us. Maybe let me start from here. So at this moment, the plate is tilted towards us a little bit, and then and at this moment, the logo is like this, right? The tip of that logo is pointing towards us. Okay. So let me play the video now. So now the face of the plate is kind of away, pointing away from us. That is originally it's like this. So now it's more like this, right? And over here, so the wobbling has completed one period, right? So originally it's like this, then sometime later back to the original orientation, right? So then we get the wobble period. So then now you ask, what about the rotation? Did it complete one cycle? So then you can notice that by looking at the logo, right? So originally, the tip of that logo is pointing towards us, right? So just now the tip of that logo is pointing away, right? So now it's like this. That is the rotation have only gone through half a cycle, right? So from this to this, half a cycle. So that is the period of rotation is double of the period of wobble, right? So that is to say, right? So the wobbling frequency is double of the rotational frequency, right? You can keep observing, right? So every time the wobble completed one cycle, then the rotation only completed half a cycle. Okay. And then so you might ask, then how fast the rotation is actually. So that really depends on the initial condition that you give to the system, right? So you can give a very fast initial rotational velocity, right? So but that will just at the same time, right? So increase the wobbling frequency. Okay. So that really depends on. So that is this omega-3 itself will depend on the initial velocity, initial condition that you give. But no matter what, there's a 2-to-1 ratio. And in fact, so in his book, so he said that he tried to calculate this, right? So, and he actually got the ratio to be 1/2 instead of 2. Okay. So and we don't really know whether he actually made a mistake or is he just treat it as a joke or something. Okay. But indeed, so it should be a factor of 2, but not a factor of 1/2. Okay. But that's not very important here. Okay, so now let me also tell you the other methods that is actually more easy to follow. The second method actually is to how to figure out this ratio of the frequency. Okay. So here we are going to make use of the formula that we had from the previous chapter. Remember, we derived this relation here, right? So the relation between the derivatives in the fixed frame and the derivatives in the rotating frame. And at that time, I told you that, right? So the A can be any vectors that describing physical quantities of your particle, right? And in the previous chapter, we just put A as velocity or acceleration. So now I'm again making use of this formula here, but I'm going to put A, right? So as L, right? So the angular momentum vector. Okay. So then if I write it this way, and then I again substitute the expression of omega and L into this equation, okay. So what I get is the following, right? So notice that, remember, right? So the external top equals CLDT, right? So that's why the left-hand side is 0, right? So that is this term plus this term is equal to 0. So if I actually just decompose this equation into 3 components, then you should get these 3 differential equations. Okay. And I'll just skip the steps of solving, but you should find that this omega 1 and omega 2 given by this. Okay. And this capital omega is given by this ratio. So this cosine capital omega t and this sine capital omega t are describing the wobble motion. Okay. And this capital omega is the wobble frequency. And again, you can see this ratio here. So I3 minus I divided by I. Okay. So that would give you the factor of 2. Okay. Okay, so let me show you just one more short animation. I think I have it here. Is that what if we don't have a plate, but another shape? So because when I derive this formula, right, so it does not have to necessarily have to be a plate, right? So as long as a symmetric top, then that's fine. So and the ratio, right? The ratio between the wobble and the rotation frequency, well, depends on depends on the geometry, right? So I get the factor of 2 is because of this I3 minus I divided by I. So if you have a shape that looks like this. What is this? So this is a ellipsoid. You can see that, right? So it's like it's a sphere, but it's compressed. It's an ellipsoid. Okay. So then I'm not actually going to calculate the moment of inertia of these shapes, right? So, but you can just consider two limiting cases, right? So if you have a perfect sphere, then you know that the moment of inertia for all three directions are the same, right? So if you just compress the sphere all the way down to become a plate, right? So then you have that ratio of 2. So that is to say, if you have a perfect sphere, the ratio should actually, what should that be? If you look at this, right? So you consider a sphere, you look at this ratio here, right? So that should be 0, right? A perfect sphere, because I1 equals I2 equals I3. So I3 minus I is just 0. If you have a plate, then you have 2, right? So therefore, if you are somewhere in between, like an ellipsoid, then you expect that you have something that is smaller than 2, but greater than 0. Okay. So then let's see. So let me start over here. Okay, this is good. So at this moment, right? So it is kind of facing us, the normal vector. And then you can look at this red line to see the rotation. So look at how this red line moves to see the rotation of this body. So let's play it. Okay. So now the wobble motion completed one cycle. And then now you can see that the red line is kind of in behind, about half, but actually it's a bit more than half. Let me keep playing this. So now the wobbling has completed one cycle. No, actually the wobbling has completed the second cycle already. So the wobbling has completed 2 cycles. So now you can see the red line, right? So almost back to the original position. Actually, it's a little bit more than the original position. So let me play one more time. So third cycle for the wobbling, and then the fourth cycle for the wobbling, right? Fourth cycle for the wobbling, and you can see this red line. The rotation has completed, well, clearly a little bit more than the second cycle. So then the ratio is not 2 anymore, and that's because of the fact that the ratio of the moment of inertia, okay, in this situation is not the same as what we had in the plate. Okay. Okay, so let's continue. So what I'm going to do next is to introduce the Lagrangian formulations. Okay, so for this rotational motion. So remember, when we talk about Lagrangian, so the first thing is to pick the so-called the generalized coordinates, right? So you need a set of generalized coordinates to describe the system, and then you write down the Lagrangian based on that set of generalized coordinates. Okay. And I think well, we have talked about some rotation problems before, even back in chapter 2, right? So I just have a rotation of a cylinder on the floor, right? So you understand that we are going to use the angle theta, right? So to be the generalized coordinate, right? So, however, now in general, now I'm allowing the rotations, right? So to be not just about a fixed axis. So as we have seen, right? So I allowed to have this so-called the wobbling motion also, right? So that is right. So in general the rotational the omega vector is not fixed anymore. Then if I have such an object, so how should I take a set of generalized coordinates to describe this kind of rotation? So, or that is to say, if I give you an object, right? So like the plate, my hand, right? So I want to describe its state. So it can be like this, right? So it can be like this, it can be like this, right? So how do I describe that using angles? Okay. So then therefore I need to introduce the concept of the so-called the Euler's angle. Okay. So what you imagine is the following, right? So suppose I have a plate or a cylinder or a cube, right? So any object. So if I want to describe its orientation at a particular time, okay, so what you could imagine is the following. Okay, so it's just that initially you are just putting everything just upright. So let's say a cylinder. Initially, let's say I'm just putting this cylinder upright. That is the axis is just parallel to the z-axis. So and then after that, I want to consider the cylinder that is oriented like this. Okay. So that is how should I describe this? So what you imagine is the following: is that you start with this, and then you just imagine that you can do a series of rotations to get to this. Okay. So then the procedure is the following. Okay. Right. So that is no matter what. When I reorient an object, so it can always be described by a series of rotations. So and that is the Euler's rotation theorem. Okay. So just consider these three pictures over here. So initially, let's say I have x, y, z coordinates. Okay. Okay. So what I'm going to describe is rotation of a coordinate system. But you imagine that the same logic can be applied to rotation of a body, right? So because we imagine that the coordinate systems, let's say, is always follow the orientation of the body. Okay, so initially I have this red coordinate system x, y, z. So the first rotation I want to do is a rotation about the z-axis. Okay, so with an angle phi. So after that rotation, you imagine that I get this blue coordinate system. Okay, so like this. So now let me now go to step 2. So step 2, I start with the blue coordinate system. So let me draw again the blue coordinate system. Like this. So what I do now is to rotate, do a rotation about the x1 axis. Right, so from the red, I have x, y, z. After rotation, I have the x1, y1, z1. So x1 is not parallel to x anymore. The step two I'm going to do is to do a rotation about the new x-axis, the x1 axis. Okay, by an angle theta. Okay. So now the z-axis or the z1 axis is no longer pointing up, instead it's pointing over here. Okay. Right, so after the second step, then I have this green coordinate system. So finally, I'm going to take this green coordinate system. I will draw it again over here. And then do the third rotation. Okay, so this time it's about this Z2 axis. Then I'll get to this orange coordinate system. Like this. Right. Rotation angle this time is this side. Right, so just try to follow the steps carefully. Right, so from originally I have the red coordinate system, and then after that I have the blue. That's the first rotation. Right, so after the second rotation, I have the green coordinate system, and finally, after the third rotation, I have the orange coordinate system. Okay. So that is, you want to try to reorient any object, right? So you can always follow these 3 steps to do that, right? So any orientation can be obtained by taking from the original orientation and then do these 3 steps. Okay. But of course, you have to choose these 3 angles correctly, right, such that you can go to your final orientation that you want. Okay, so now you can see that, right? So I can describe the state of this object. Okay, so using these 3 angles, and these 3 angles will be our generalized coordinate. And notice one thing, so when I do this, right, so you can see that the origin of the coordinate system is always fixed at the same point. That is what we imagine is that the center of mass of the object, right, so it's always at that point. Okay, so and with these 3 angles, how do we describe the angular velocity? Right, so remember what I told you about the infinitesimal rotation in part 1 of this chapter. Right, so if this just imagine that the object, right, so perform an infinitesimal rotations. Okay, so with these 3 angles, right, so within a very short time, infinitesimal time dt. Right, so that is from t is here, and then after dt is what we have over here. Right. So then the omega vector can just be expressed in this way. Right. Because infinitesimal rotations follow the rules of vector addition. Right, so remember that, right? Therefore, right, so using these three angles, I can write it as a vector with three components. And now just be very careful about these three unit vectors. What is x1, what is z, and what is z prime? Okay, just follow this diagrams over here. Okay. And in fact, well, you can see that these three are actually not perpendicular to each other. Okay, but that's okay. You can still write your angular velocity vector in this way. And in fact, just from the geometry in this page, you can express this x1 and this z in terms of the x prime, y prime, and z prime. Okay. Therefore, if I just write everything in terms of x prime, y prime, and z prime, then you will write the angular velocity vector this way. Okay. So the x prime, y prime, z prime are the unit vector of the orange coordinate system. Okay. Okay, so now we know how to express this angular velocity, right? So using these three angles or these three generalized coordinates, then that means we will be able to write down the kinetic energy of this body, right? So using these three generalized coordinates. Okay. So actually, in general, if I talk about the rigid body, this rotation is one thing, right? So but the other part you know already would be the translational motion, right? So that translational motion, you will need another three coordinates to describe, right? Just the x, y, z position of the center of mass, let's say. Right. So then you will need that three, and then also the three angles, the Euler angles that I just talked about. So that is in total, you need 6 generalized coordinates to describe your rigid body. So however, in the example that we'll consider, the center of mass of the body, okay, so is at rest, or a particular point of the body is fixed. Okay, so then in that case, we will still only just need the three angles to describe the whole body. Okay. So that's one remark here, is that I told you that a rigid body need 6 generalized coordinates. Okay, so but is there another way to think about why it is 6? Right. So you can just start from the viewpoint of a system of particles, actually, right? So if you have one particle, how many generalized coordinates you need? 3. Right. So now if you have a rigid body formed by 2 particles, how many generalized coordinates you need? if you just have two particles, you should need 6, right? So, but because of the fact that this is a so-called rigid body, so that means that this distance is fixed. That is, you do need 6 if it's not rigid body. But now you're talking about rigid body, so you minus the number of constraints. Right, so this concept I told you before in chapter 2, right? So how many generalized coordinates you need, right? So it depends on number of particles times 3 minus the number of constraints. But so in this case, I have two particles to 6 minus the 1 constraint. That is 6 minus 1. So this is 5 actually. So but this is just a rod, right? So not really this kind of bodies that we are considering, right? So once you go up to 3, then you see how the 6 comes in, right? So if I have 3 particles, right? So then what you should do is add 3. However, constraint. So to form a rigid body, you need to fix this distance and this distance. So then I minus 2. Then 6 minus 1 plus 3 minus 2. So that is 6 actually. So what if you keep doing this? The 4th particle. If you form a rigid body, right? So you should again draw the rods. So do I need to draw 3 rods this time? So actually no. As long as you have draw 2 rods, like this one and this one, then that's sufficient to form a rigid body. Right? So you don't need this one actually. So that is whenever you add a new particle, well, so you add 3 more generalized coordinates, but at the same time, you add 2 more constraints. So that is sorry, I said something wrong. So actually, you do need to form a rigid body. Okay, so you do need 3 rods, right? So because you need to fix it in the 3-dimensional space, right? So that is like this. But 3 is enough. Okay, so that is you need to fix 3 relative distance. Then you fix the point in the 3-dimensional space. So that is when you add the 4 particles, you add 3 coordinates, but then you also add 3 rods. So then 3 constraints, right? So the 5th particles, right? So again, you just need 3 rods. So again, plus 3 minus 3. So that is once you get to 6 generalized coordinates, and then you keep adding particles, you are just keep doing plus 3 minus 3. So you are no longer adding more generalized coordinates. Okay, so now let's find the Lagrangian. So the kinetic energy, in part 1 of the chapter, I already find this general expression, right? So it's 1/2 omega dot L. And remember this L, right? So it's the I omega. Okay, so now when we do this, remember the coordinates axis are always overlapping with the principal axis of the bodies, right? So therefore, again, I can write it as this diagonal matrix. So then this is the expression for the kinetic energy. Okay. So what about the potential energy? But potential energy is actually easy, right? So because, well, at least for the gravitational potential energy, just mg, it doesn't matter how ugly the shape is, right? So if you calculate the potential energy, you just need to pick your center of mass, see the height, and then multiply by mg. And in fact, I'll consider the these two cases. U equals 0 and then U equals mgl cosine theta. Okay. Actually, I think I'll just focus on the second case. Okay, because for the first case here, actually is the it would be equivalent to the wobbling plate example that we just did. Okay, so let me show you the problem that I want to show you. Is this symmetric top? Okay, so the spinning top. Okay. Right. So the whole thing is spinning, but again, you can see kind of this wobbling motion. Okay. And here, in the example, we will make an approximation, make a constraint that the bottom point, the contact point, let's say is always fixed. Okay, so that is this point. So this thing is allowed to spin. Okay, so but this point is not allowed to move. That's the constraint that we're going to apply. Okay, but before that, let's just show you the form of the Lagrange equations. Okay, so the Lagrange equations really is nothing new. Okay, so but just to use the exact same form of Lagrange equation, right? So no matter how complicated it is, right? So for your set of the generalized coordinates, right? So but the form of the Lagrange equation is still the same. Okay. So therefore, if I do that, then so just one remark here. Okay, so L here means Lagrangian. Okay, so not angular momentum. Just take the derivatives, you get these three equations of motion. You can see that in general, they won't be easy to solve, right? So they're coupled together, and also it's nonlinear. There's a square term over here. Okay, so motion of the spinning top, as I just show you the video. Okay, right? So it is spinning, but at the same time, right? So this axis is moving like this. So this motion is called the precession. So in this case, okay, so the potential energy of the system is given by mgl cosine theta. So L is the distance between this point and the point of center of mass. Okay, like this. Okay, so now I'm going to consider a special case where the theta is not changing over time. So that is this angle not changing over time. Okay. So then that is I have this theta dot is 0. Okay. Then if I just go to plug in the theta dot, right? So it is 0, and then consider the equation of motion over here. Then I get the following. Okay. So because of the fact that theta dot is 0, so that means you are saying that phi double dot is 0. And that is phi dot is a constant. I call this the capital omega. And in fact, this capital omega is the angular frequency of the precession. Okay. And finally, by this equation 3, again putting the left-hand side to be 0, then you see that from here I can find out the capital omega. And there are actually two roots. One is fast precession, the other is slow precession. And the slow precession is the one that is usually observed. And in fact, if we allow the theta to also vary, let's say just vary slightly over time, it can be shown that theta would be approximately given by a sinusoidal function. And that leads to the phenomenon called nutation. Right, so that is this theta is also changing like this over time. But I'm not going to go to that in detail. Okay. Actually, I do have one more note that I want to talk about. Maybe I'll just go through that real quick. So actually, do you know that our department has a YouTube channel making this science education video? So those are, I would say, most of the contents are too easy for you because those are probably for high school students. But there's one video that's actually relevant. But I'm not going to play it over here. But you can go back to watch it by yourself. But this is about spinning top. Okay, so you might want to check it out after the lesson. Okay. Okay, so I want to briefly mention. Okay, I only have 5-10 minutes left, but it is actually related to one question that one of you asked me earlier in the semester. Is that what if I consider some force that cannot be expressed in terms of the potential energy that we are familiar with? And actually, the example that we can think of is magnetic field. Okay, so electric field, for electrostatic field, you can define an electrostatic potential, right? So, but in general, for a magnetic field or even a magnetostatic field, you might not be able to define a potential energy associated with that. And that would be related to this. Okay, so again, this won't be in the exam. But what I'm trying to say here is the case where the potential energy depends on the so-called, depends on velocity. And this is the so-called the velocity dependent potential. So first of all, I think you might feel a bit confused because potential energy, by definition, is the integral, right? So force dr, right? So that's how you pick the potential energy. Okay, so then how, from using this definition, so of course you understand that the potential energy is not depending on the velocity. Okay, but anyway, so let's say when I talk about velocity dependent potentials, you have to first of all forget about this definition first. Just forget this, and just accept the fact that okay, so there is a thing called the velocity dependent potential, and then the Lagrangian is still defined by kinetic energy minus potential energy, and then you can still use the same form of Lagrange equations to work out the equation of motion. Okay. So that's the thing, right? So the velocity dependent potential. Okay, so forget about the original definition. Okay. What we are requiring is that there is such a thing. Okay, so such that I can input it in the Lagrange formulation, then everything still works the same way. Okay, so if I indeed have a potential energy that is depending on the velocity, then this is the Lagrange equations that you will write down. Okay, so if you don't have the velocity dependent potential, you don't have the red term, and then this one alone is the generalized force. This is something that you are familiar with already, right? So, but now if you have this velocity dependent potential, then this whole thing, these two terms added together, will be defined as the generalized force. So that is what I'm trying to do is the following. So now I have to just imagine the magnetic force. I have the magnetic force, and then I want to write, so the magnetic force here, I want to write that in terms of these two terms added together. And that U would be the velocity dependent potential. Okay. Right. So how should I write down the expression of U? Right. So such that the Lagrangian formulations work exactly the same way as what we used. And that should be able to give us this form of equation of motion. Right. So if the Lagrangian formulation is correct, it has to still give us what we are familiar with, like this one. So then the key is the following. Okay, so in your 2041, you have learned the following, right? So is that if you take magnetic field, so just focus on the time independent magnetic field, just because that's what you have learned before. So if you do this surface integral, right? So over a closed surface, the flux of magnetic field is always have to be zero. Right, so that's the general property of magnetic field. And in fact, this is one of the Maxwell equations. And by using divergence theorem, you still remember that, that would imply that the divergence of B has to be zero everywhere. Right. And mathematically, if you have a vector field that has no divergence, then that means that vector field can always be written as the curl of another vector field. So therefore, B can be always written as the curl of A. This is another magnetic, another field. And this A is known as the vector potential of, it's known as the vector potential. And if I give you a vector potential, you take the curl, then you get magnetic field. So that's the definition of vector potential. Okay. Okay, so now, okay, so the vector potential itself still is not velocity dependent. Okay, so let's say B is a function of x, y, z. Then A is also a function of x, y, z. So no velocity is involved yet. Okay, so however, so let's now let's put this B equals curl of A into this equation. So this is the Lorentz force law, right? So then your equation of motion is written like this. Okay, so I don't think I have enough time to really finish this, but so what you do is that if you just take the right hand side, okay, so and just play with the derivatives, okay, manipulations with this vector calculus. Okay, so no any new physics concept here, just play with the derivatives. Then eventually you should be able to make this force term as this form. Okay, after playing with all these derivatives. And now this form, the first term with the partial x and the second term with this d dt, that's exactly what we want, right? So that is because I told you in the beginning, right? So the generalized force with the velocity dependent potential take this form. First term with this partial derivative, second term with this d dt. So then, therefore, this thing, also this thing, is the velocity potential, velocity dependent potential that we are looking for. Okay. So it's written as Q times V minus V dot A. So if you don't have magnetic field, right? So then this is just the A is just 0. So then this Q V. So that's just the electric, so static potential that you know of, right? So now you have this minus V dot A. Okay. So then the Lagrangian would becomes this. Okay. Okay, so again the kinetic energy now minus the potential energy, but this potential energy is what we have, right? So the velocity dependent potential. And one interesting thing here is that if you just go ahead use the same definition to find the generalized momentum, then you realize that this P is not just mv plus QA. Okay, so then this is a important situation. Okay, so where the generalized momentum is not equals to the kinetic momentum. Okay. And over here, I have to skip this exercise, but and after you get the Hamiltonian, Lagrangian, you will be able to also get the Hamiltonian. Okay, so using the same definition as we always use. Okay, so remember how did we got the Hamiltonian from the Lagrangian, right? So it's always equals to this, the summation of pi qi minus L, right? So if you try to use this definition, you should be able to verify that Hamiltonian written like this. Okay, so I think I will have to stop here now. Okay.